Okay, so some vocab on the front. These are called rational functions and their graphs. Some of them will look like what we've been doing, like 1 over x minus 3, where we had 2 branches. But some of them will look a little bit crazy. Any rational equation is written in the form where you have an equation where the top and the bottom are polynomials. So for the past few days, we've been doing ones where the numerator was just a constant number and the denominator was a polynomial. Today we're going to see x's in the top and the bottom of the polynomial. So for example, x squared plus 4x over x squared minus 16. So guess what's going to come back into play? Factoring. Factoring. Yay. Somebody reminded me yesterday that I never gave the pop factoring quiz.
No, you did.
He didn't mean to. I don't think you ever gave that, and then it reminded me. So everyone's yelling at him. We won't say names. But you'll get factoring on your next few quizzes with this unit anyway. So this is an example of a rational function. Sometimes the graphs will have discontinuities. We've seen the imaginary line, the asymptote. Today we'll also see what are called removable discontinuities, which are little holes in the graph, so a little point that can't exist. Your table and graphing calculator will help you because you'll usually see an error in the table, so you'll know that that's a point of discontinuity. Continuous graphs are graphs that have no jumps, breaks, or holes. So, like when we did parabolas, that would be an example of a continuous graph because it didn't have anything that was being skipped. When we're doing discontinuous graphs, obviously those have a jump, break, or a hole, and you can see 3 visually of what we're looking at. The first one is a point of discontinuity that we've been looking at, an asymptote. This would be a vertical asymptote. Here's the example of a point of discontinuity. This is like one we've been doing recently, right? 1 over x minus 3, x minus h, therefore x cannot equal 3. Now, the way that you're going to do this, there's not necessarily a formula for your discontinuities, but we will know that the discontinuities occur when the denominator equals 0. If the denominator is equal to 0, you'll have a discontinuity because dividing by 0 is undefined or illegal to do. So in this example, 1 over x minus 3, if you take the denominator, bless you, and set it equal to 0, add 3 to both sides.
Please excuse the interruption. Charles Johnson, please report to the office. Charles Johnson, please report to the office. Thank you.
Okay, and this is a vertical asymptote because it's the equation x equals the number. And you can look, this is the actual graph of that function. The second type is called a removable discontinuity. A removable discontinuity is a point that can be removed by factoring and simplifying the numerator and denominator. The whole of the graph will be filled with like an open circle to show that it's you're skipping over that point. So in this example, we would need to factor the numerator. What will this factor into? X squared minus 16. Difference of squares. What? X plus 4 and x minus 4. The denominator was not factorable. It's already a linear term. But you can divide out the pair of common binomials to simplify so that the equation is now f of x equals x minus 4. Which to graph this, that's just a linear function. Start at -4, up 1 over 1, up 1 over 1, back from algebra 1. The good old days. But you'll notice on the graph there's a hole. Now when you look on your graphing calculator, it won't show visually, but in the table you will see one. Okay? The hole occurs, and this is called removable because you removed it by canceling them out. The hole will occur at what you removed from the denominator. So the hole would occur when x plus 4 equals 0, subtract 4, so the whole is at negative 4. The mistake I'll see you guys make is that since it says x equals negative 4, you'll draw in a vertical line, like an asymptote. That's not necessarily the case. This is a point. So you need to make this into an ordered pair, negative 4 comma something. To figure out what that y value is, you plug the x value into the simplified equation. So negative 4 minus 4 would get me that the whole right here is at negative 4, negative 8. It's also called a jump discontinuity because you're jumping over. So let's type this in the calculator just to show you guys what it'll look like. Type the original one in, and you'll need parentheses. X squared minus 16. Never type the final one in because that's not going to show you the whole that we eliminated. Okay? So make sure you're always typing in the original. X squared minus 16 divided by x plus 4. Again, group the top and the bottom. Anything with a plus or minus needs grouping. And zoom 6. Now when you graph it on your calculator, you don't see the whole. It looks like it's a straight line. A slanted line. A line. When you go to the table, second graph, you will notice at negative 4 there's an error showing that there is a discontinuity. So a lot of you will use the table to help you find the discontinuity too and make sure you did it right. But just be aware that the graph is not going to necessarily look how your graph should look. You have to have that whole drawn on your paper. Again, these are called removable because they canceled out. And so it just left a little dot instead of having a whole asymptote. The non-removable discontinuities are what we've been doing. Those are your asymptotes. So in this example, you can factor the denominator into x plus 2, x minus 2. But nothing divides out. You don't have any common binomials in the top and the bottom. So since nothing is able to cancel or divide out, we'll actually have 2 discontinuities. It's when the denominator is equal to 0. So basically set each of those things equal to 0 and solve. You'll get x equals negative 2 and x equals positive 2. These are actually vertical asymptotes, which are also known as discontinuities, just another word for them. And when you look at this graph, it's really crazy looking. We haven't seen anything like this yet. But you have your 2 vertical asymptotes here. You have a branch on this side. You have like an oddly shaped parabola. It's not really a parabola because it's not symmetrical, but it's kind of like a little curve here. And then another branch. Okay, you're not going to have to graph these by hand. You'll always have your calculator to assist you, but you will need to be able to find out the asymptotes, and then you can use the table to sketch the graph. Okay? But they do, some of them will look really bizarre if you have a lot of asymptotes going on. Just to talk about the domain, I guess. The domain for these will be all row numbers, but you'll have 2 exceptions. So you would say except x cannot equal positive or negative 2. And you can just put like a comma and list them, so you don't have to write x does not equal multiple times. Okay. Tomorrow we're going to continue this idea. Tomorrow we'll learn how to find the y, the horizontal asymptotes. In the last unit it was always y equals k, but these are not going to necessarily be in that formula, so these aren't 1 over a. They're different formulas. So tomorrow we'll learn how to do that. That's really the only new piece of information for those of you missing. There's a chart with rules to memorize. So we have a couple that we're asked to graph and identify our discontinuities. So first of all, can we factor the numerator or the denominator? No. Always try to do that first. So then we're going to go to stating our discontinuities, which is, again, when the denominator equals 0. So we're going to take the denominator, x squared, and set it equal to 0. And solve for x. Square root both sides. Technically you need a plus or minus, but 0 isn't positive or negative. So you'll get x equals 0. Is that a removable or a non-removable discontinuity? Did we cross anything off? Canceling out? No, so it wasn't removable. It's non-removable, which means it's a vertical asymptote. So go to x equals 0 and draw in a vertical asymptote. Now this one, you can use your calculator, of course, to get your table, but this is really easy to plug in mentally too. If you plug in some numbers, just do some quick mental math. Negative 3 squared is 9. So when you plug this in, you have 1/9. Negative 2 squared is 4, so that would be 1/4. Negative 1 squared is 1. 1 over 1 is just 1. 0 squared, 1 over 0 is going to be undefined. So when you go to the calculator, if you check it, it'll say error. So you know that's your discontinuity. And we'll get 1/4, 1/9. Again, you don't have to do this by hand, but since the numbers are so easy to calculate, why not? Go ahead and plot this. So normally when we were graphing these the past 2 days, they were in like opposite quadrants, like one was above and one was below. These are both above. Okay, so it's going to be a little bit different because we have an x squared in the denominator. Let's also type it in our calculator just so we can make sure that when we sketch the graph, it does look basically what it should look like. Again, today we don't necessarily know how to state the horizontal asymptote yet. Tomorrow that's part of the lesson, but you can use your calculator to see that it does kind of level out here, so it looks like it's not going to go below 0. So we'll just take and, oh, whoa. Where that came from. Go to that. And sketch. So you have that vertical asymptote in the middle, kind of almost like an axis of symmetry. All right, so let's look at a couple more that have factors. Same description, we're going to state the discontinuities and graph them. Are we able to simplify the equation before doing anything else? Is there anything we can simplify out? Yep. We have matching binomials. Divide them out. As soon as you divide something out, that tells you that this is going to be a removable discontinuity because you're removing it by canceling or dividing out. So we're going to say x minus 2 equals 0, x equals 2. But that is not a line. If it's removable, it's called a hole. So you need to make it into an ordered pair, 2 comma something. To figure out what that something is, we'll plug 2 in for x. 2 plus 1 is 3. So this is a hole in the graph. I usually graph those first so I make sure I don't make it look filled in. So 2 comma 3, put a nice open circle. Now to graph the rest of the function, you're more than welcome to use your graphing calculator, but I think we know how to graph x plus 1. Right? Start at 1, up 1 over 1, up 1 over 1, don't fill that in, up 1 over 1. Now, if I'm allowed to use my calculator on my quiz, I'm definitely checking this to my y equals before I turn it in, make sure I did it right. So let's check this in the graphing calculator. Again, when you're checking it, you want to type in before you cross stuff off to make sure. So use parentheses, x plus 1, x minus 2, divided by. Now you don't need an extra set of parentheses around the 2 things on the top. You can put that if you want to be safe. Now if there were 2 things on the bottom, you would need to group both of them. And we might see one of those later. Press our graph button. Again, the hole is not going to show up. It's going to look filled in, but when we go to our table, you'll see that at 2 there is an error. So you can see that it's clearly not part of your domain. Okay? That's a discontinuity occurring at 2, 3. All right, in example 3, can we simplify anything out? Can we cross off the x's? No. Good. So nothing's able to be simplified, so we have no removables. We have a non-removable. And non-removables are also called vertical asymptotes. So those are going to be equations. X equals the number, which is going to be the opposite of this by setting it equal to 0. Add 2. So go and draw a vertical asymptote for our discontinuity that cannot be removed. And then you could do a table of values by hand, but since there's x's in the top and the bottom, it's a little bit harder. So you may just want to use your graphing calculator to do that for you. Save some time. This one kind of looks more like what we've been doing. Again, tomorrow you will learn how to find the horizontal asymptote by looking at the equation. Just by comparing the degree of the numerator and denominator. But for right now, you can clearly see the vertical asymptote. Looks like there's a horizontal asymptote at maybe like 1, but we're going to find that out for sure tomorrow. To plot some of these points, just go to the table and pick some of them to plot. So maybe like -4.5. You don't have to write these down, you can just plot them, but for the notes purposes, maybe I'll pick -1, 0, 0, -0.5, 3, 4, 1, -2, 3, 4, and 5, 2. Just to get some. You can plot more if you want, but just to be able to get that idea of what's going on. So once I plot those 4, I think that's pretty much enough to get a sketch. And on the other side, 3, 4, and 5, 2. Not agree. Oops, I didn't plot that at 2. Plotted that at 1. But again, after tomorrow's lesson, we'll have a little bit more information to make these more precise.
Is there any way to make it so that whenever I go to my tables, there's more than just like a few numbers? Like,
Yeah, your table, we've modified our table sometimes so that we could type stuff in. So if you want to change your table, go to Table Set, second window, and change both of those to auto. Make sure the starting number is an integer too. Like if you wanted to count by something different, you can change that to, if you want these on auto. If they're on ask, then you have to type numbers in to see the numbers. All right, the last few, we are not going to have to graph them, just state the points of discontinuity. The clock finally is right, okay. So again, the first thing you want to do for your problems like this is factor, because sometimes you might be able to cancel things out. What can I factor the denominator into? Crazy? X plus 2 and x minus 2. And then they ask us a ton of questions for these, I'm sorry. So nothing is removable because we can't cancel anything out. So we're going to have 2 points of discontinuity. And it does want us to state, so this will be non-removable discontinuities at where? Willie? X equals 2 and at x equals -2. Again, since they're non-removable, they stay equations, not points. If they're removable, then they're a little dot that you have to find the y value for. So these are also known as vertical asymptotes. You don't have to write that, but just so if you were graphing, you understand what these stand for. Determine if any of the, or we did that part. State the domain. The domain will be all real numbers except the points of discontinuity. So all real numbers except x cannot equal -2, 2. You can graph this too if you want. You don't have to, but some people like to put it in their graphing calculator. Then we have to find the x and the y-intercepts. We'll do this by hand, but some of you like to do this on the calculator. The x-intercept is the harder one. The y-intercept is the easier one. Let's do the y-intercept first. Y-intercept is when x is 0. So go up to the original equation or the factored equation, it doesn't really matter. Plug in 0 for x. 0 squared is 0, minus 4 is negative 4. 1 over negative 4 is negative 1/4. So this would be 0, comma, negative 1/4. Y-intercept, always your friend. X-intercept, more algebra. We'll use some of that white space over here. The x-intercept is when y is 0. So you're actually going to plug in 0 for y. And it doesn't matter really if you use the factored form or non-factored form. Let's use the non-factored because it's smaller. You have to undo division with multiplication. So you're dividing by this whole quantity, so you need to multiply by this whole quantity. What happens when you multiply this by 0? It's just 0. 0 times anything is 0. So you're going to get 0 equals 1, which it doesn't. So that means that there is no x-intercepts. And that will happen sometimes. It doesn't actually cross the x-axis. Probably because there's a horizontal asymptote telling you that you can't touch that. You also could graph it, and you can probably observe that too. The next one, can we factor the top or the bottom? Someone I haven't heard from yet today. How would I factor the top? X squared minus 1. X plus 1, X minus 1. Very good. How about the denominator? Sheila. You can't factor it because it's a plus 1. Very good. Not factorable. So we can't cross anything off. We cannot divide out. So these are going to also be non-removable because we can't remove anything. If we have any, I should say. I'll write non-removable. So again, just like we did in the last one, we set the denominator equal to 0. This time we're going to have to take this quadratic and set it equal to 0. So solve for x. Subtract 1. Square root. Plus or minus. What's the square root of negative 1 again? I. Do we get imaginary things on our graphs? No. So you can cross that off, and you're actually going to tell me that there are no discontinuities. There's no numbers. There's imaginary numbers it's not allowed to be, but those don't affect our graphs here in a real coordinate plane. So step 2, there's no restrictions on the domain, so it's just all real numbers. We can graph this too if you want to see what it looks like. X-intercept and our y-intercept. And let's do the y-intercept first since it's the easy one. If you go back and plug 0 in for x, you can do it in either the factored form or the non-factored form. You'll get 0 squared minus 1, which is negative 1. 0 squared plus 1, which is positive 1. And when we divide those, we'll get negative 1. So this would be 0, negative 1 for my y-intercept. The x-intercept is our harder one. So plugging in 0 for y. I'm going to use the factored form this time. If you don't, you'll just have to factor it again. Just like in the last one, we undid division with multiplication. Do that first. So we get 0 times this stuff is still 0. However, we don't have a number on the right-hand side. We have 2 binomials. So the zero product property says that if these two things equal 0, either one of them is 0 or the other of them is 0. So you're actually going to get two x-intercepts, setting each one of them equal to 0 like we did back in chapter 5. We should get -1 and +1. So you actually have two x-intercepts, -1, comma 0, and +1, comma 0. And if you want, you can graph that, and you can probably see them faster than doing all that work, too. We have time, let's graph it. Go to y equals and type in the original. You'll need parentheses. Weird looking. Rational functions can get you some really weird looking graphs. Sometimes you can put them together and make shapes by graphing multiples. But you can see, and maybe you guys are like, hey, Mrs. Bennett, I don't want to do all this work, so I'm just going to go ahead and type it in my calculator. Go you. You get a calculator on the whole quiz. All right, try example C. Using your calculator or doing it by hand, answer all of the 4-part questions. Your discontinuities.